And one thing I will say first off is that a lot of what we did for graphing polynomials last class is going to carry over to graphing rational functions this class. So rational function looks like this. It's some function f of x equal to a polynomial divided by another polynomial. So the top and bottom have to be both polynomials, meaning they have to be functions of x where all the powers of x are positive integers. So here are a few examples. F of x equal to, what do we got here? X squared over x to the 6 minus 1. Right? The numerator is a polynomial of degree 2. The denominator is a polynomial of degree 6. It's a rational function. Top is a polynomial, bottom is a polynomial. That's it. Or something like g of x equal to x squared plus 1 over 3x squared minus 1. Also a polynomial, degree 2, sorry, also a rational function. Degree 2 polynomial on the top, degree 2 polynomial on the bottom. And thirdly, I have x cubed over 3x squared minus 1. H of x equals x cubed over 3x squared minus 1. Oh my goodness. Excuse me. Sorry about that. I actually want to write one more just because. So again, degree 3 over degree 2 polynomial, it makes a rational function. And I'll even write one more, f of x equal to 6 over x to the 4th plus 1. Also, do they have to have the same degree? They do not, for sure, right? This is x squared over x to the 6, definitely different degree. They just both have to be polynomials. Here they have the same degree. Here they have a different degree, right? The top is 3, the bottom is degree 2. And here the top is a degree 0 polynomial. So I really should have said non-negative, not positive powers. Okay, so this is a rational function as well because the top is a 0 degree polynomial and the bottom is a 4th degree polynomial. So all of these are examples of rational functions. Yeah. And what else do I have to say about this? So we can use, so we're going to do the same kind of stuff before. So to graph them, we will find x and y intercepts just like we did before. And again, there might not be any of either of these things, right? There are definitely rational functions that we have already graphed that don't have any y-intercepts or x-intercepts. One example of that would be the rational function f of x equal to 1 over x. That's definitely a rational function. The top is a polynomial of degree 0. The bottom is a polynomial of degree 1. Since it's a polynomial over a polynomial, it is a rational function. We've graphed this before. I'm going to graph it again just so you guys can see it. Right, this is this graph here where you have a horizontal asymptote at y equals 0, a vertical asymptote at x equals 0, and you have no x-intercepts and no y-intercepts. So sometimes these graphs don't have any intercepts. We still should check for them. Okay. So one thing we're going to do, or I should say two things we're going to do when we graph these rational functions is look for y-intercept and x-intercepts. There are also two other things we're going to look for because a lot of these, not all of them, but a lot of them are going to have asymptotes. So, vertical asymptotes. This pen could go. So vertical asymptotes, which I often abbreviate as VA. This pen's not much better. All my red pens kind of just out. So a vertical asymptote is a vertical line. Vertical. I can spell, I promise. Vertical line. So it's something like x equal to c. And when we find the vertical asymptotes, what we do is we set the denominator of the expression equal to 0. So we set the denominator equal to 0 and solve for x. Because what we have seen, or what we will see, is that vertical asymptotes essentially occur when the function is undefined in such a way that the denominator is 0 and the numerator is getting non-zero. An example of this would be, say, f of x equal to, what do we got here? X squared over x plus 2 times x minus 3. So to find the vertical asymptotes, I would set the denominator equal to 0. So I'm going to set x plus 2 times x minus 3 equal to 0. And then I'm going to find all the solutions. So the solutions are going to be x equal to negative 2 and x equal to positive 3. And if I was graphing this, which I'm not going to do right now, but if I was graphing this, I would have a vertical asymptote. A vertical line at x equals negative 2 and a vertical line at x equals 3. Again, that's not part of the graph. It's kind of one of the boundaries of the graph. I feel like there's more I want to say here. Maybe not. We should have more room because I'd like to write more stuff down here, but I don't think I have the room to do it. So let's go back. Let's go to the other side. And actually, for a second, before we get going too quickly here, let's actually look at, none of these examples are really that great. So if I look at this one right here, I can see that there are two vertical asymptotes. The denominator for this one is x to the 6 minus 1. And if I set x to the 6 minus 1 equal to 0, there are two solutions, x equal to positive 1 and x equal to negative 1. So this function, we have a vertical asymptote at positive 1 and at negative 1. And I wish I didn't have to erase these right now because the thing, I guess I may still talk about these even though I'll erase them, I might write them again. I want to talk about their horizontal asymptotes. Horizontal asymptotes, it's interesting. Horizontal asymptotes, I think, are a little bit more challenging to think about, but it's once you kind of have got it down, they're really easy to find. So let's talk about horizontal asymptotes. Oh, I should say one more thing. Generally, and certainly for rational functions, the graph of a rational function, or really any function for the most part, never crosses a vertical asymptote. And it's because the function's undefined there, right? We can't really cross it if it can't be, we can't find a value for the function at the vertical asymptote. So let's talk about horizontal asymptotes. Horizontal asymptotes. Gosh, my spelling today is really good. And let me just check one thing, make sure my video doesn't look too shabby here. Yeah, no, we're good. All right, cool. So for horizontal asymptotes, you're not setting anything equal to 0. Instead, you have to compare the degrees on the top and bottom. So a horizontal asymptote is a horizontal line like y equals c. And to find them, we compare the degrees of the polynomials on the top and the bottom. The degree of the top versus the degree of the bottom. And there's actually 3 separate cases here. So the first thing that can happen is if the degrees are the same. So if the degree of the top is equal to the degree of the bottom. Like the example, so in fact, this kind of circles back around to the thing Jonathan wrote in the chat. Do they have to have the same degree? Well, no, they don't, but something special happens if they do have the same degree. So the example I had written that had the same degree was, I forget what I called it. I think I called it h of x equal to, what have we got here? X squared plus 1 over 3x squared minus 1. So if the degree on the top and the degree on the bottom are the same, which they are here, the degree here is 2, the degree here is 2, then the horizontal asymptote is going to be y equal to the leading coefficient on top divided by the leading coefficient on the bottom. So it's the leading coefficient of the top divided by the leading coefficient of the bottom. In this particular case, the horizontal asymptote for h of x equal to x squared plus 1 over 3x squared minus 1 is going to be, well, let me ask you guys, what is the leading coefficient on the numerator? Well, you've answered the final question, Jonathan. Yes, the final answer is 1/3. The leading coefficient in the numerator is 1, and the leading coefficient in the denominator is 3. And again, I'll remind you, sometimes people are going to write things out of order. So the leading coefficient isn't always what shows up first. It's the coefficient of the thing that has the highest power. So if I instead wrote, that my function was, say, g of x equal to 2 minus x squared plus 4x cubed over x to the third, x to the second, plus 6x cubed minus x. The degree on top and the degree on the bottom are the same, right? The highest power on top is 3, the highest power on the bottom is 3. So the horizontal asymptote here would be y equal to the leading coefficient on the top is 4, leading coefficient on the bottom is 6. So it'd be 4 over 6, which reduces to 2 over 3. So just be careful, right? Leading coefficient just means the coefficient of things to the highest power. But then there are two other things that can happen. If the degree on top is less than the degree on the bottom, then the horizontal asymptote is 0. We've actually seen an example of that, right? 1 over x. We definitely graphed it as a horizontal asymptote of y equals 0, and the degree on top is less than the degree on the bottom. But another example could be something like f of x equal to x plus 2 over 3x squared plus 1. Degree on top is 1, degree on the bottom is 2. Oh, the degree on top is less than the degree on the bottom, we have no horizontal, or we have a horizontal of y equals 0. And then the last thing is the reverse. If the degree on top is bigger than the degree on the bottom, then we have no horizontal asymptote. Yeah. And so the thing that's true about a horizontal asymptote is that as the values of x get larger and larger, or more negatively large, like as we go way out to the right or way out to the left, as that happens, the function values, the y values, get closer and closer to the horizontal asymptote. And we'll definitely see that when we start graphing things. So let's graph some things. Yeah. And so if you look at the notes online, there's kind of like a 4-step process maybe for graphing things. And I'm definitely going to kind of follow that because that's the way I usually do it. So typically when I'm graphing a rational function, so we're going to graph the function f of x equal to x plus 6 over x minus 2. The 4 steps I follow are the following. I personally like to start with the y-intercept. No, I'm not looking at, sorry, I'm looking at I would prefer to look at the notes I wrote. Yeah, cool. So yeah, I usually start with the y-intercept just because it's easy. All right, so first I'm going to do the y-intercept. After that, I'm going to find the x-intercepts. Again, you might find none. After that, I usually like to find the vertical asymptotes. And then finally, the horizontal asymptotes. So that's what I'm going to do. I should also point out I'm also going to think about the multiplicities of the x-intercepts like we were doing for polynomials, because that's kind of useful. So y-intercept, set x equal to 0. All right, so if I plug in 0, if x is 0, f of 0 is going to be 0 plus 6 over 0 minus 2, which is 6 over negative 2, which is negative 3. So my y-intercept is 0, negative 3. For the x-intercepts, so for the x-intercepts, we're going to set the whole thing equal to 0, and then we're going to do something really, really kind of right away. So we're going to set the whole thing, x plus 6 over x minus 2 equal to 0. And then we're going to immediately multiply both sides by the denominator. So I'm going to multiply the left, I'm just writing this. I'm going to multiply everything by x minus 2. So on the left-hand side, when you multiply a fraction by its denominator, those denominators cancel. And we do this here, oh yeah, that's going to cancel out the x minus 2, and we're just going to get x plus 6. On the right-hand side, what's x minus 2 times 0? Oh, it's 0, right? Anything times 0 is 0. So here's what actually always ends up happening when you're trying to find the x-intercepts of a rational function. You're really just looking for where the numerator is equal to 0. Because that's the only way a fraction can actually ever equal 0, is if the top is 0 and the bottom isn't. So if x plus 6 is 0, x has to equal negative 6. So we get the point negative 6, 0. And then I would point out additionally that x equal to negative 6 came from the factor x plus 6, which it isn't written this way. It is x plus 6 to the first, which means that x-intercept has an odd multiplicity. Has a multiplicity of 1, which means we're going to cross when we hit that x-intercept. Okay. Vertical asymptotes, we're going to set the denominator equal to 0. And we're going to end up getting x equal to positive 2. Horizontal asymptote. Is the degree on top the same as the degree on the bottom? Yes, right? They're both 1. Degree on top is 1, degree on the bottom 1. So the horizontal asymptote is y equal to the leading coefficient on the top over the leading coefficient on the bottom, which in this case, the leading coefficient on the top is 1. The leading coefficient on the bottom is also 1. So it's going to be 1 over 1, which is 1. Great, I've got all the things. Now I'm going to graph it. Put this pen in the pile in a second. Is that enough? Probably. I need to go further left with my negative 6 there. Okay. So what do I have? I have a y-intercept of negative 3. Right there. An x-intercept of negative 6. I have a vertical asymptote of positive 2. Draw that in black. And that's x equal to 2. And I have a horizontal asymptote of y equal to 1. And then we try and graph it. So here's what I know is going to happen. So there isn't really end behavior to consider here, or at least I should say there is end behavior, but it's the horizontal asymptote that kind of is defining the end behavior. So I know that I go way out this way, the function's either going to get close to the line that way or that way. Similarly, as I go way out that way, we're going to get close to the horizontal asymptote either that way or that way. So let's see. I'm going to start my y-intercept. And this is a good thing to know. As I move towards my vertical asymptote, I either have to get negatively infinitely large or infinitely large. Which way do I have to go? Is there a reason why I maybe couldn't go up this way? Does anyone want to unmute themselves and volunteer? Yeah, you're right. It definitely is. It definitely does. So I will agree with everyone that it has to go this way. But what I really want, so that's a good answer, Jonathan, but it's actually not the right answer. So you guys both have the right idea, But I want to really stress, because this is super duper important, we can't cross a vertical asymptote, but there are lots of functions that cross their own horizontal asymptotes. And I'll show you one in a minute. But this one doesn't cross its own horizontal asymptote. Here's the thing, though. There's something else we can't cross. So if I was going to try and go this way, what are the two things I'm crossing as I go up? Yeah, there's the horizontal asymptote. What's the other thing I crossed on my journey upwards?
The x-axis.
The x-axis. Why can't I cross the x-axis? I don't have an x-intercept, right? I don't have an x-intercept at, 0 or 1 or 2 or anywhere in between there. My only x-intercept is -6. So if you don't have an x-intercept, you can't be crossing the x-axis. It's just, that's the way it is. So what I really, really, really want you to take to heart is that when you're trying to determine which way you're going as you get closer to a vertical asymptote, you should be ruled by the fact that, I'm not allowed to cross the x-axis unless there is an x-intercept. In this case, I can't go that way because there isn't an x-intercept. I will also say, though, and we're going to encounter some functions where, yes, you not only can you, but you have to cross your own horizontal asymptote sometimes. Okay. And then on the other side of this, so I could either be going this way and getting close to the horizontal asymptote, or this way. But I have to be going this way because if I were going that way, I would have to cross the x-axis to be able to get closer to my horizontal asymptote. And again, I don't have an x-intercept over here. On the other side of the y-axis, we have to go this way. We have to get to our x-intercept, we cross, and then we keep getting closer and closer to our horizontal asymptote. And again, my picture maybe doesn't look the best, but that's how it looks. I will also point out, my picture doesn't look very good on the notes either. Let's do some more examples. Unless there, I should say, are there questions about this one before we do some more examples? Okay, hearing no questions, let's do another one. We'll do another similar one, actually. We'll do an extra one that's not in the notes just right now. I'm going to try to do this next one kind of quick. So let's look at, say, f of x equal to 2x minus 6 over x plus 2. Sure. So again, we're going to find the four things very quickly here. Y-intercept, set x equal to 0. F of 0 is going to be 0 minus 6 over 0 plus 2, which is -3. Same as last. Let me make sure I didn't actually do like the same function. No, it's different enough. Yeah. Okay. X-intercept. We could set the whole thing equal to 0, but we're really just going to set the top equal to 0. So 2x equals 6, x equals 3. Vertical asymptote. Set the denominator equal to 0. X plus 2 equals 0, x equals -2. Horizontal asymptote. Is the degree on top larger, or is it the same? Or is it smaller? It's the same, right? The degree on top is 1, the degree on the bottom is also 1. So a horizontal asymptote is y equal to 2 over 1, right? The quotient of the leading coefficients, which is 2. Let's throw it all in the coordinate system. Let's see. Let's see what we've got. We've got intercepts, a y-intercept at -3, just like last time. An x-intercept at +3. A vertical asymptote at -2. And the horizontal asymptote at +2. Okay. And I am typically the kind of person that likes to start at my y-intercept and move to the right. So as I move to the right, I have to hit my x-intercept. And then you could either figure out that you have to cross because the x-intercept of 3 came from the factor 2x minus 6, which is all to the first power, which means it's an odd multiplicity every cross. Or you could say, well, I have to cross because if I don't cross, there's no way I can get closer and closer to this horizontal asymptote. That's kind of the rule, is that as you go way out to the right or way out to the left, the function has to get closer and closer to the horizontal asymptote. All right, everybody. As we go to the left from this y-intercept, we have a choice. And obviously I've drawn the graph already kind of light, so it looks like it's supposed to look. But our choice is either to go down to negative infinity or up to positive infinity. Which way do we have to go? Up or down?
Down.
Down. But really the thing I want to ask is, why can't we go up? What can't we cross?
X-intercept.
Well, the x-axis, because we don't have an x-intercept. But yes, that's exactly the right idea. Right? We cannot go up because there's nowhere in here that we have an x-intercept where we can cross the x-axis. Great. So now on the other side, our function, and I'm going to draw it two different ways. Our function could either do this or do this. But eventually, right, you have to get closer and closer to this horizontal asymptote. And one of these isn't allowed because one of these has an x-intercept where we shouldn't have one. So it can't be this one. So if you use kind of what you have, and more importantly, what you don't have to graph the thing, you are very kind of limited in your choices. The other thing you could do if you don't love all this, like maybe you're like, I don't really know if I go down or I go up, you can plot extra points. You can say, well, I'm going to plug in, x equals -1 over here. If you plug in -1, you get -2 minus 6 is -8 over -1 plus 2 is 1, and -8 over 1 is -8. So at -1, like I get -1, -8. And that's a little more clear. Oh yeah, it is going down over here. And then you could go further left and plug in like -3. If you plug in -3, you get -6 minus 6 over -3 plus 1, which is -12 over, sorry, -3 plus 2, which is -12 over -1, which is positive 12. So yeah, oh, at -3, I'm getting positive 12. So you can do that if you're like, I'm not really sure if it's above the x-axis or below the x-axis. I'm going to pick another point to plot to help me figure out which way it's going. That is a perfectly fine thing to do. All right, let's look at some more examples. What I'll say though is you definitely want to find these four things. You definitely want to find the y-intercept if you have the y-intercept singular, only one, if you have one. The x-intercepts, plural, if you have any. The vertical asymptotes, you might have more than one. And the horizontal asymptote, you can only have one. I should say, for rational functions, you can only have one horizontal asymptote. You will see functions in calculus that actually have two different horizontal asymptotes, one to the right and one to the left. But not rational functions. Rational functions, if they have a horizontal asymptote, they only have one, and it's the same right and left. Okay, so let us do this next one. F of x equal to 2x squared over x squared minus 1. Minus 1? Yeah, minus 1, sure. All right, let's do all the things. Y-intercept. Set x equal to 0. So if x equals 0, y is going to be f of 0, which is 2 times 0 squared over 0 squared minus 1. 2 times 0 squared is 0. 0 minus 1 is -1. What's 0 divided by -1? 0. 0 divided by any non-zero number is 0. 0 divided by 0 is a subject we leave to calculus. 0 divided by 0 is an indeterminate form, which means it can end up being anything. And you'll definitely see a lot of 0 over 0 when you start talking about limits when you take calculus. X-intercept. So here's what I know. I got a y-intercept of 0. So my y-intercept is 0, 0. I know that's also going to be an x-intercept, right? If the origin is a y-intercept, it's also an x-intercept. There might be others though, so I still double check. So I'm going to set, and again, I could set the whole thing equal to 0, but I know that's just going to result in setting the top equal to 0. Does anyone want me to say more about that? Because I am happy to say more about that. Okay, so how are we getting that? The way we're getting that is by saying, okay, I'm going to set, really I'm setting, so again, right, when we find the x-intercepts, I should back up. When we find the y-intercepts, we set x equal to 0, right? Because you're saying, oh, I'm trying to figure out where I'm on the y-axis. Well, that means x has to be 0 because I haven't moved left or right. For the x-intercept, we set y equal to 0 because we're trying to figure out, oh, I don't want to move up or down, so y has to be 0 because I'm somewhere on the x-axis if y is 0. So I'm going to set y equal to 0. So I'm saying, okay, the y part here, or the f of x part, is 0. 0 equals 2x squared over x squared minus 1. But then what I'm going to do is I'm going to multiply both sides by this denominator. And here's the thing. When you multiply a fraction by its own denominator, those denominators cancel out. And what's 0 times x squared minus 1? Anybody? Yeah, thank you. Exactly. So here's what happens. Every time you set this fraction equal to 0, you multiply both sides by the denominator, and then you're just left with the numerator on one side, but it's still 0 on the other side. So you can just cut out the middleman and say, oh, I know I'm going to end up setting the numerator equal to 0. You can always go through the process of setting the whole thing equal to 0, but if you want to save yourself a step, you can say, oh, I know it's going to be the top equal to 0. And so if I solve this, I'm then going to divide both sides. I mean, really the solution is just 0, right? I've got 2x squared equal to 0, divide both sides by 2. 0 equals x squared, and then you could square root both sides with the square root of 0 is still just 0. And I do want to point out that this x-intercept came from a fact that it has a multiplicity of 2. So it's going to bounce instead of crossing there. So x equals 0 is our x-intercept, but it's got a multiplicity of 2. All right, and then we need our asymptotes. Our vertical asymptote we get by setting the denominator equal to 0. So I set x squared minus 1 equal to 0. I'm actually going to get two solutions. We get x squared equal to 1. X is equal to plus or minus the square root of 1. Square root of 1 is 1. So I get plus or minus 1. Two vertical asymptotes. One at positive 1, one at negative 1. Horizontal asymptote, I definitely have a horizontal asymptote because the degree on top is 2 and the degree on the bottom is 2. So the degrees are the same, and the horizontal asymptote is y equals leading coefficient on the top over the leading coefficient on the bottom, which is 2. Does that say m2 next to 0 equals x? It sure does, for a multiplicity of 2, meaning that it's going to bounce off the x-axis at that x-intercept instead of crossing like the previous ones. Yeah, good question, Jonathan. I was talking about back the other day about how you shouldn't say good question, because when you say good question, it means like, if you don't say good question for every question, then it means like the other questions weren't good questions. I don't mean that when I don't say good question to your good questions. I just, sometimes I'm like, oh yeah, that really, like, so the questions have all been good. Thank you for the questions. So, yeah, she's like, you just shouldn't say good question because there's no value there. I'm like, okay, fine. I'll try not to say good question then. It's hard because the questions are good questions. I like your questions. All right, so let's see here. So I've got y-intercept and x-intercept at 0. So that's just about 1 point there. And then I've got a horizontal asymptote at 2. And vertical asymptotes at positive 1 and negative 1. Okay. Something I want to stress, because I've definitely seen students kind of go wrong with this before, is basically you should have, except for at the x, besides the vertical asymptotes, there should be a function for every other value of x. So from here to here, there should be a function either up here or down here. From here to here, there should be a piece of the function, somewhere. From here to here, there should be a function. You shouldn't be missing pieces. So the problem with having the origin is I don't know from here if I have to go up or go down, because I don't know that I can't cross a horizontal asymptote. That is not true. I could maybe cross this horizontal asymptote. So what do I do when I don't know? Well, I'm going to go ahead and pick a number that's between 0 and 1. So if I plugged in 1/2 for x, the y value would be 2 times 1/2 squared, which is 2 times a fourth, divided by 1/2 squared, which is a fourth, minus 1. I don't really care what this is. I mean, it's 1/2 over negative 3/4, which ends up being, I don't even know. I really don't care. I just care that it's negative, right? The top is positive, the bottom's negative, and a positive divided by a negative is a negative. So that I know that when I plug in 1/2, I get out a negative number. So that I have to go this way. And since I know it bounces here, it also has to go this way. All right. On the other side of this vertical asymptote, you have to have one of two things happen. Either has to be going up to infinity or down to negative infinity. But it can't be down, because if it was down, I'd have to come up this way. I'd have to cross the x-axis where I don't have an x-intercept to continue getting closer and closer to this horizontal asymptote. So it has to look like this. Or if you don't like that, you can say, well, I don't know what's happening over here. I'm going to plug in 2. If I plug in x equals 2, I get y equals, let's see, 2 times 2 squared over 2 squared minus 1 is 2 times 4 is 8. 4 minus 1 is 3. Yeah, when x is 2, y is 8/3. So it has to be positive there. And then the same sort of thing is happening on this side. It has to be like this. I should point out, this is an example of an even function. There is symmetry across the y-axis. If you flip this around, do a horizontal reflection, it looks the same. Or if you want to check it on your own, if you plug in negative x for x, this function doesn't change. Right? 2 times negative x squared over negative x squared minus 1 ends up being the same as what we started with. So good example of an even function. Okay, yeah, let's do, I think I got time for at least one more. Yeah, let's do that one. Yeah, that looks funky. No, I don't like that so much. Let's, yeah. Okay. Yeah, I really, I'm going to do a different one. Not you. Let's do you. Yeah, cool. All right. So let's do this one. So I'm going to skip the second to last one on the what we did in class notes. OW 2020 is what I'm looking at. And I'm going to graph this one, the last one. Y equal to 2x minus 6 over x plus 2 squared. Again, we find all the things. Y-intercept. Set x equal to 0. Y is going to equal 2 times 0 minus 6 over 0 plus 2 squared, which is negative 6 on top, 2 squared on the bottom. That reduces to negative 3/2. Or negative 1.5 if you like a decimal. Nothing wrong with decimals. There is something wrong with getting water all over my table, though. That's terrible. And then let's see, x-intercept. Or intercepts. There could be more than one. There isn't, but there could be. Set 2x minus 6 equal to 0. We get 2x equal to 6. We get x equal to 3. Vertical asymptote. X plus 2 squared equal to 0. So x plus 2 equals 0. X equals negative 2. And finally, horizontal asymptote. Okay. So let me ask you guys. This is actually, so I want some answers. What's the degree of the polynomial that's on top?
1.
Thank you. Yes. Harder question. Not a lot, but a little. What's the degree of the polynomial on the bottom?
2.
Right, because if you multiply it out, you get x squared plus some other stuff. So the degree on top is less than the degree on the bottom, which means our horizontal asymptote is y equal to 0. Which is hard to draw because it's just the x-axis, but that's fine. We don't really draw it, I should say. So let's plot all the things. We've got a y-intercept of -3/2, which is -1.5. So that's halfway between -1 and -2, so right there. Got an x-intercept of +3. I've got a vertical asymptote of -2. And I should have given myself a little more room over here. Yeah, I really should have. Sorry. I need to give myself more room there because there's something that happens over there that I want you all to see. So let's do this instead. Yeah, that'll be good. Sorry about that. Okay, and maybe myself a little more room too. Okay, so again, the same stuff that I already plotted. I've got -3/2 for my y-intercept. I've got -2 for my +3 for my x-intercept. -2 for my vertical asymptote. And 0 for my for my horizontal asymptote, which I can't draw, right? My horizontal asymptote's right there. I can't draw a dashed line on top of a regular line, right? It's not going to change anything. Okay, so now, again, starting at my y-intercept, I'm going to move towards my x-intercept, and I am going to cross. And you can either see that you're going to cross by the fact that this thing that the x-intercept came from is to an odd power. Or you can pick a number that's over here bigger than 3, like 4. If you pick 4 and you plug in 4, 2 times 4 is 8, 8 minus 6 is 2, that's positive. And 4 plus 2 squared is definitely positive, and a positive over positive is a positive. So as I go this way, I have to cross. And I'm going to leave it there for a second, we'll come back. As I go this way, well, again, I have to go down to -infinity because I cannot, although I can cross a horizontal asymptote, I cannot cross an x-axis without an x-intercept. So we have to go that way. Now, the question is, what happens on the other side of this vertical asymptote? Are we going up like this, or are we going down like this? I don't know, because there's nothing over here to tell me any more information. So at this point, I kind of have to just plug in a point and say, okay, well, if I pick like -3, and I plug, well, yeah, -3, right? So plug in -3. Well, first and foremost, the denominator is always positive. Anything squared is going to be non-negative, I should say, but positive in this case. -3 plus 2 is -1. -1 squared is +1. If I plug in -3 to the top, you get 2 times -3, which is -6. Minus 6 is -12. So it's a negative over a positive, which is negative. So it is down here below the x-axis being negative. So it's going to look like this. And not like this. And then I'll have something else to say, yeah, I got no time. Now here's the thing. Over here, I know I have a horizontal asymptote at y equals 0, which means as you go way out this way or way out that way, the function has to be getting closer and closer to that line y equals 0. So what has to happen is somewhere over here, and we don't know where because we don't have the tools yet, but somewhere over here, I'm going to draw this again. I'm going to do that. Sorry, make this a little bit nicer. Somewhere over here, you're going to turn around and get closer and closer to your horizontal asymptote. I don't actually touch the x-axis again. I just get closer and closer to it. I want to point out that this graph does cross its horizontal asymptote. Horizontal asymptote's right there, y equals 0, and we cross it right there at that x-intercept. So it is perfectly natural and okay for a function to cross its own horizontal asymptote. It doesn't happen all the time, but it does happen sometimes. The other thing I want to say is that we could have, if we wanted to, seen that the behavior around this vertical asymptote was like this, because this vertical asymptote came from a factor that has an even degree. When you have an even degree, both sides do the same thing. They either both go down or they both go up. Whereas when you have a horizontal asymptote, a vertical asymptote that comes from an odd degree factor, and this does, because x squared minus 1 factors as x minus 1 times x plus 1. Each of those vertical asymptotes, 1 and negative 1, come from factors with odd degrees. And so each of those do opposite things on either side. All right, that's all I've got. There is a